Hello everyone, this is Jenny. I'm a doctoral candidate at the Lynch School of Education, Boston College. I'm so happy to be invited here as a last speaker of the Brownback lecture series. Today I'm going to talk about multilingual automated scoring in international large-scale assessments. This is a table of content. First of all, I will briefly talk about the background of automated scoring in international large-scale assessment. And then I will move to research questions, methods, result, and conclusion of this research. Okay, so here is the background. In 2019, the teams marked the transition from paper-based to computer-based testing. Approximately half of the participating countries transitioned from paper-based to computer-based testing. One great advantage of computer-based testing is that it allows for the wider use of open response format items, including constructed response items, or CR items. Even though it has been known that well-designed or well-crafted CR items can be very useful in terms of assessing students' higher-order thinking skills, their use has been strictly limited in ILSAs in international large-scale assessment compared to the traditional multiple-choice items. The main reason for such limited use of CR items is closely related to the nature of human scoring. Then what is the nature of human scoring? First of all, it is resource intensive. In other words, it is labor, time, and cost intensive. Human scoring of CR items includes several steps of procedures, including scoring guide development, training of human readers, and scoring work. Given that ILSAs usually involve a huge amount of multilingual responses, it is never easy to human score those large amounts of multilingual responses. And second nature of human scoring is that even with extensive training, there still remains some possibilities of radar effects or even inconsistency. Humans are not perfect, and therefore, depending on the human reader's fatigue, leniency, or severity, or even depending on the human reader's perception or understanding of the rubric, the human scores can be different. Because of these characteristics of human scoring, the use of CR items in ILSAs has been limited. And if the limited use of CR items is closely associated with the human scoring nature, then why don't we consider the use of automated scoring? Why don't we consider the use of machine to score those CR items? And actually, automated scoring in education is not new. It has rich history starting from Alice Page's Project Essay Grader in 1966. There has been a number of approaches toward automated scoring, such as ETS's E-Rater, Pearson's Intelligent Essay Assessor, and these days there is Duolingo's English Test. However, even though there has been a number of approaches and there has been long desire to automate scoring, automated scoring in ILSAs is still lacking. In other words, automated scoring in the multilingual context still remains largely unexplored. It is because scoring a very large amount of multilingual responses in ILSAs can be very challenging. In the case of teams, more than 60 countries participate, and it includes all different 50 languages. It is a combination of many languages and many responses problem, and in ILSAs of more than 100 versions of the test exist. So the application of automated scoring in the multilingual context remains challenging. Even though there has been several machine scoring engines in the mid to the late 1900s, those early machine scoring engines heavily depend on the manual feature selection or handcrafted rules. So application of those early scoring engines to ILSAs can be very time-consuming and costly. So we wanted to examine the potential of automated scoring combined with the state-of-the-art machine translation and artificial neural networks. The research question is here, so how to improve automated scoring in ILSAs using artificial intelligence? More specifically, we wanted to examine whether automated scoring can be applied accurately and consistently across multiple languages and across multiple countries. Okay, let's move to the methods of this research. First of all, dataset. We used 6 short constructed response items from the TIMSS 2019. These 6 items are homogeneous in terms of the target grade and subject domain. They are grade 4 science items. And these items are dichotomously scored, so 0 score is given for the incorrect response, and 1 point was given for the correct response. And these items are released items that are available upon request. And the multilingual dataset includes 1 English language and 7 non-English language countries. More specifically, Matthias, I can hear your typing sound. Could you mute yourself? I'm sorry.
Makes sense.
Yeah, yeah, thank you. Uh, and the dataset includes 4 Latin alphabet-based languages and 2 non-Latin alphabet-based languages. And we followed 5 steps of procedures, starting from data preparation, multiple machine translation, pre-processing and bagovers, training and testing artificial neural networks, and the last step was model evaluation. And this is the example CR item that I have analyzed for the study. So when you see the item here, it is the item stem or item question is straightforward and simple. And also this scoring rubric shows how to classify student responses into correct response and incorrect response. And one characteristic of short CR items is that it expects students to include certain keywords or key terms to be considered as correct response. In this item here, evaporate, dry, or water vapor are the keywords for a correct response. And let's move to the procedure. Step 1, data preparation. In the case of TIMSS 2019, approximately 200 student responses were double-scored by independent human raters. Although we used all responses for individual countries, we wanted to take advantage of those double-scored responses. Assuming that if 2 human scores agree with each other, those responses and scores are more trustworthy, we doubled the responses with which 2 human scores agree. However, the responses with which 2 human scores disagree were removed from the training dataset because it is uncertain which score should be regarded as a true score. Table 1 on the right side shows the example of the human scoring. When we see the first 2 student responses here, we can see that 2 human scores agree with each other. These 2 raters scored the first response as correct response, and these 2 human raters scored the second response as incorrect one. So we doubled these responses in the training dataset. However, when we check the last 2 responses here, we can see that first human rater scored these responses as correct response. However, the second human rater did not give any credit to these responses. Such misalignments probably comes from the misspelling in the student response. Here, evaporates and evaporate, they are the misspelled version of the evaporate, and probably the first human rater might be more generous in terms of misspelling. However, second human rater might be more strict in terms of addressing misspelling. So in this case, it is uncertain whether which score should be considered as true, so these cases were removed from the training dataset. And the whole dataset was built into training data versus test data at the ratio of 80% versus 20%. Step 2 is multiple machine translation. Even though machine translation has been around for decades, recent machine translation has made rapid progress. Big tech companies such as Google, Facebook, or DeepL, they provide affordable, fast, and high-quality translation. Even these days, OpenAI's GPT models, pre-trained large language models, are considered as excellent translators. Even though the GPT models such as ChatGPT or GPT-4 are not originally invented for the translation, the researchers these days found out that GPT models can provide high-quality translation for any language pairs. So in this study, we decided to use multiple machine translation rather than relying on a single machine translation to achieve more high-quality translation. Specifically, we used Google Translate and ChatGPT API for translating non-English language responses into English. This figure shows how we were able to build huge cross-language and cross-country dataset in English. So here we can see the non-English language responses, and these responses were machine translated into English. And then the translated responses here are merged with the English language responses. So we were able to build this huge cross-language, cross-country dataset in English. And the benefit of this approach is that we do not need to construct different training dataset for each individual language. We can use the huge dataset here across languages. And here, the figure 2 shows the NLP solutions and languages. Multiple machine translation can be especially useful for handling low resource languages. Here, low resource languages indicate the languages that have much less data available for constructing any kinds of natural language processing solutions or packages. And when you see the left graph here, currently, most NLP solutions are exclusive to English. Almost 70% of the NLP solutions or packages are designed for English, and we only have 6% of NLP solutions designed for low resource languages, even though more than 3 billion speakers use low resource languages. So, building a single cross-language dataset in English using machine translation would be the most feasible strategy to score multilingual responses in ILSs, because currently most solutions are exclusive to English. And before moving to step 3, I'd like to talk a little bit more about prompt engineering in relation to ChatGPT. When we used ChatGPT for the translation, we tested a number of different prompts to obtain the desired outcome from the ChatGPT. Prompt engineering is a very important part to produce desired outcome from the GPT models, not just ChatGPT model. And prompt indicates the instruction that tells what the model should do with the given information. And prompts should be very clear and effective instructions. On the right side, you can see the best practices for prompt engineering with OpenAI API. OpenAI provides the guidelines for the best practices for prompt. So according to the guideline, we can test different prompts and figure out which prompt works best according to our needs, according to our goal. Now, here is the example of less effective prompt and better prompt. Less effective prompt says that the description for this product should be fairly short, a few sentences only, and not too much more. It is too vague and too general, so it is less effective to achieve our desired outcome. However, when you check the better prompt here, it says use a 3 to 5 sentence paragraph to describe this product. So it is more straightforward, clear, and effective. So it is very important to test different prompts and find out the best prompt that works with our research. I think many of you here already heard about ChatGPT or have some experience with ChatGPT. And in my case, when I tried different prompts, playing with the playground was very helpful to find out the most suitable prompt. When you log on to the OpenAI website, you can see the playground banner, and you can see the system, user, and on the right side, there are some parameters we can adjust. And system here, this is the part where you put into your prompt. And user part, this is the input, so you can provide your dataset or text here. And on the right side, you can select the mod or model, or you can change the parameters depending on your needs. And we adjusted the temperature parameter from zero point 0.7 to zero point 0.2. And here, temperature parameter governs the randomness of the output. So the temperature of 0 indicates that outcome will be more straightforward and more deterministic, and temperature of 1 indicates that the outcome can be more random or more creative. In our case, we do not want random translation, we want more straightforward and clear translation, so we lower the temperature value from zero point 0.7 to zero point 0.2. And here the prompt inputs are the parameters. So we can play with the prompt input and parameters to figure out the best prompt and best parameters. Okay, let's go back to the step 3, pre-processing and bagovers. A set of pre-processing was applied, including tokenization, lower casing, spelling correction, and stemming. And here we adopted our unique spelling correction method rather than simply replacing the misspelled words with the correct spelled word provided by the default spelling correction package in Python. We built spelling correction dictionary from the training dataset, and then we replaced misspelled words in the test dataset with the correctly spelled words in the training dataset. This will be able to provide more context-appropriate spelling correction. So this is the spelling correction method we adopted. And after the pre-processing, the key feature matrix was extracted from the bagovers model. This is the scoring rubric we reviewed, and we can see that evaporate, dry, and water vapor are the keywords for a correct response. And as a result of bagovers, we were able to capture those keywords, evapor, water, dry, or vapor. So this shows that we can extract the key concept or keywords using the bagovers model from the training dataset. And it is beneficial to apply the same key feature matrix across countries because it can ensure more consistent scoring in the multilingual context. And step 4 is training and testing artificial neural networks. There are different versions of the artificial neural networks, but we decided to use fully connected feed-forward neural networks, which are generally structured into input layer, hidden layer, and output layer. FNNs are generally provide acceptable performance and it is very fast, so we decided to use this model. And on the right side, figure 5 shows the overall architecture of the fully connected feed-forward neural networks. So first part is the input layer, second part is the hidden layer, and the last part is the output layer. And the circles are neurons, and we can see that in the input layer, word 1, 2, 3, and 4 are designated as each neuron. So the number of neurons in the input layer is equal to the number of key features from the bagovers model. So for example, if we have 10 keywords extracted from the bagovers model, then we have 10 neurons in the input layer. So the numbers are equal. And the next part is hidden layer. This is the main part that computer algorithm is realized. The number of neurons and weight decay are optimized. And the last part is output layer. We have single neuron here, which is machine score. So it will produce 0 or 1 depending on the student response. If the machine classify a student response as incorrect one, it will generate 0 for that response. However, if machine classify a response as incorrect response, it will generate 0. Yeah, so 0 for the incorrect one, 1 for the correct response. We also implemented cross-validation with the training dataset. Step 5 is model evaluation. So how we can evaluate the performance of automated scoring, how we can evaluate whether it is doing good job or not. To measure the performance of the automated scoring, we checked out the proportion of the classification agreement between human and machine scores. Table 2 on the right side, confusion matrix shows that there can be 4 different outcomes as a combination of machine score, and human score. So we focused on the proportion of both incorrect and both correct out of four possible outcomes. If machine score agrees with the human score, we can say that machine is doing good job. However, if machine score and human score do not agree with each other, we can think that machine is doing something wrong, or even possible, it is possible that there is something wrong with human score. So as a measure of model evaluation, we focused on the both incorrect and both correct proportion. Okay, and then let's move to the result of the study. In the initial part of this presentation, we pointed out that one important nature of human scoring is that it is resource intensive to be applied to illnesses. And this study found that automated scoring could be more resource efficient compared to human scoring. First of all, machine translation and artificial neural networks were time efficient. When we translate non-English language responses to English, both Google and ChatGPT took less than 1 second per student response. More specifically, Google just took 0.14 seconds and ChatGPT took 0.42 seconds per response. So it is very fast and time efficient. And when running the artificial neural networks, it took 10 to 15 minutes per item. So we learned that it is very time efficient. And second, machine translation and artificial neural networks can be cost effective. Google charges $20 per million characters, and ChatGPT charges $0.002 per 1,000 tokens. Here, 1,000 tokens is equal to approximately 750 words, so ChatGPT is quite affordable compared to other GPT models. Also, artificial neural networks can be run using open source software such as Python or R. In this study, we used Python, and installing the Python and using the NLP packages in Python are totally free. So we can learn that in terms of time and cost, automated scoring is resource efficient compared to human scoring. And automated scoring is not just time efficient and cost effective. We found that automated scoring provides comparable performance to human scoring based on the high quality translation. Both Google and ChatGPT generally provided high quality translations across countries and items. And one observation was that ChatGPT slightly outperformed Google Translate, especially at handling spelling correction. When there is a misspelled word in student response, Google was able to provide appropriate translation for some responses. However, for some student responses with misspelled words, Google was not able to provide appropriate translation. In the case of ChatGPT, it was more able to provide more context-relevant, more appropriate translation for the student responses, even if it has some misspellings. Table 3 shows that the example of machine translation into English. The first column here shows the original Korean response, and the second column is the translated response from Google Translate, and the third column here is the translated response from ChatGPT. And the red colored words indicate that these are the misspelled words. And for the first, second, and fourth one, these student responses do not have appropriate spacing. So first, second, and fourth, they have problems with spelling and in terms of spacing. For the first two responses, both Google and ChatGPT were able to provide appropriate translation. However, for the third and the last one, I noticed that Google translation is inappropriate. However, ChatGPT was able to provide more context-relevant translation based on the question. So even with the misspelling and no spacing issue, ChatGPT outperformed Google, yeah, in general. Furthermore, we found that the Bagel words model appropriately capture the key features from the training dataset. In other words, it means that important keywords for a correct response were appropriately captured. On average, we have 125 key features per item, and applying the same key feature matrix across languages can ensure more consistent scoring in the multilingual context. This is beneficial because automated scoring can mitigate scoring inconsistency, which is one of the important key challenges of human scoring. And this matrix shows how Bagel-Verse model process student responses. So each row here indicates student response. So we have yeah, 48, 33 student responses here. And the columns here indicate the key features extracted from the Bagel-Verse model, like add, all, and all the way down here, you and your. So these are the key features from the Bagel-Verse model. And the zero, we have values of 0 and 1. 0 indicates that the keyword does not show up in the student response, and the number 1, value 1, indicate that the corresponding key feature shows up in the student response. So for example, for the second student response, we can tell that water and with appear one time in the second student response. So it is very intuitive and easy to understand how the key features were extracted and works. And the final item by country classification agreement was based on the ChatGPT translation text because its performance was slightly better than Google Translate text. On average, the classification agreement across items and countries was 0.92, and at the item level, the average agreement ranges between 0.89 to 0.97. At the country level, the classification agreement ranges between 0.91 to 0.95, and we were able to achieve the agreement as high as 0.99. And then we wanted to find out or identify potential causes of misalignment between human and machine scores. Broadly, we classified the causes of misalignment into three categories: errors in human scoring, errors in machine scoring, and true score uncertainty. First one is errors in human scoring. It indicates that human score is wrong or incorrect, while machine score is correct. Humans are not perfect, and therefore human scores could be inconsistent or even inaccurate. So there, there was one item that asked us to write down the key concept of increasing heart rate. And some student responses simply include high numbers such as 150 or 160, and some human readers score those responses with only numbers as correct response. However, in another country, some human readers score those responses simply with numbers as incorrect response. So this is an example of how errors in human scoring occur in the multilingual context. And the second category is errors in machine scoring. Errors in machine scoring can be caused by multiple reasons, including translation issue, data quality issue, or the model issue. In our case, we used the Bagel-Verse model, and Bagel-Verse model is based on the word frequency. So very low frequency keywords were not captured in the Bagel-Verse feature matrix, so the machine scored the responses with uncommon keywords or the responses with very low frequency keywords at incorrect response. So there was one source of errors in machine scoring in our case. However, in the future study, word embedding or WordNet-based lemmatization could be considered to identify and address a variety of synonyms. So that was the another source of errors in machine scoring. And the last category was about true score uncertainty. There are some borderline responses that can be considered as correct or that can be considered as incorrect depending on the human reader's judgment. For example, um, there were some responses that are misspelled, however, that have phonetically very similar sound to the correctly spelled words. Generous human raters score those misspelled words as correct response because their sound are very similar to the correctly spelled words. However, the machine scored those responses as incorrect because it is misspelled. In this case, it is not sure whether which score should be considered as true score. So even though there is a misalignment between human and machine score, it is hard to decide human is right or machine is right. So these are the three categories of potential causes of misalignment. And this shows that obtaining the perfect human and machine score agreement is unattainable because there can be various reasons behind the misalignment between human and machine scores. Rather, the main focus of automated scoring should be more on whether machine can provide more accurate and more consistent scores in the multilingual context, rather than targeting the perfect agreement between human and machine scores. And the conclusion and future studies here. So the study found that the combination of machine translation and artificial neural networks can allow for the wider use of constructive response items in illnesses. It is promising approach because automated scoring has great potential for resource efficient and more consistent scoring. And we believe the next step is using this technology for quality control to help to determine whether a second human rater is needed, or we can use this technology to support human scoring of CR items in LSAS. And also future study is encouraged based on this research as a starting point. We can include more CR items and we can include more multiple languages to test the feasibility of automated scoring in the multilingual context. And especially, it will be important to study the low resource languages that have much less data available in the online platform, such as Arabic or Macedonian. So it will be important to examine the potential of automated scoring for those low resource languages. So this is the overall research presentation of mine. I think I ran a little bit fast. These are the references, and yeah, any questions or comments will be appreciated.
Yeah, thank you so much. There's
Yeah,
always already one raised hand. Ebru actually has a question.
yeah.
Directly jump
Uh,
into the
Hi,
discussion.
everyone. Good to
Yeah,
see
good to
everyone.
see you.
Thank you
Hello.
very much. This is a very exciting work. I enjoyed the presentation. I wanted to ask how this work handle or approach to the issues around data privacy.
Mm,
In a way, maybe it's on my part, maybe it's a misconception, but as soon as I hear GPT, so once we provided all the responses to AI, aren't all the responses are out there and therefore vulnerable to issues around data privacy? How do we comply with the data privacy in this type of work?
Yeah, good, very good question. So the responses are very short, and the machine doesn't see anything but the response. So there would be whatever, a short sentence, maybe in very many cases 3 words, 5 words. There wouldn't be any student IDs. There wouldn't be any indication where the response came from. So I'm sure we need to monitor that and what they actually do with that, but they get like trillions of requests every day. They can't save all the responses and they have no identifiable information. But of course, you can draw a worst case scenario and you could say, well, some student would write their address and their phone number and their credit card numbers in there. That you can filter out. So we are talking here with essentially small scale exploration, so we can still look at them. You probably need some form of intelligent filter that filters out all personal names or something like that and replaces them with whatever curly braces name, so that whatever any reference to any specific person would be replaced, anything that looks like a phone number would be replaced. So you can do this through pre-processing.
Yeah.
But you would really just feed the raw response there, and that is coming without any individual identifier. So there's really nothing out there where you could identify people. The other answer to that is, I hope ChatGPT is just a transitional monopoly. I would assume that this technology becomes very much more localized, so that you can actually run this on whatever your AI workstation or something like that. So that would solve itself in 1 or 2 years. So for me, that's not a reason to say, oh, we cannot use it. We have to be careful, and we have to make sure that we don't provide any personal information. So, but there's no student anywhere attached to the response, and many of these responses are exactly the same. These are short response questions.
Yeah.
So among the 4,000 students who answer this in whatever Korean, 500 students would give you the same answer. So how do you identify which is which? That's another question. So I think it's somewhat, I see the point. Yes, we have to make sure, but we also thought about this, and we certainly we don't feed the whole data set. We just feed the raw responses without any, there's no connection to the student in a nutshell.
Right.
Yeah.
Well, thank you for your response that and noting that no IDs are out there, just the responses. And it's good to hear that some kind of, in the future, some kind of filtering and pre-processing might be feasible to introduce to the to the work. Thank you.
And for example, what's also done when we talk about IEA giving data to countries, the process data is also similarly filtered. So where essentially anything that is identifiable would be just filtered out. So, and honestly, given past experience, very few students actually type in their phone number or their credit card number. So it usually doesn't happen.
Yeah, I think it is really good idea to consider the one part of the pre-processing could be to review any kinds of personal information. So we can include that as a part of the pre-processing, and that will be helpful to, yeah, avoid any kinds of privacy issues. Yeah, thank you.
Other questions?
But there are some,
something in the chat?
yeah.
This is Henry. Can you hear me, Jenny?
Yep.
I have a question.
Yes, I do.
Yeah, this is really great work, as you know, I've said before. I wonder, just looking into the future, what do you see as interesting additional challenges as we move to more constructed responses that have greater complexity with, say, rating scale, where you might have 3 or 4 different score levels? What do you see as, do you see there as exponentially more difficult challenges, or is it just linear in the number of response categories?
Yeah, thank you for that question. Yeah, currently we are focusing on the binary classification, but when we increase the scope to, yeah, like three category classification, I think that could be a little bit more challenging because there might be some more borderline responses between like 0, 1, and 2 credit. So I'm really excited to like explore more like, yeah, three maximum score questions or that, but I think there might be some more attention should be paid to classify those, yeah, like borderline answers. I think that could be the most tricky one we need to handle in the future. Yeah.
Thank you.
Yeah, thank you.
That and maybe if I may add, the humans also have more problems with this. So the human scorers also not
Yeah.
doing so well with partial credit kind of scoring guidelines.
Yeah. Yeah, I think the borderline answers are really tricky even for humans, and yeah, even same for the automated scoring. Yeah. Okay. Yeah, I think
But
we have
I think
the.
if I could just continue there, I think that certainly understand the problem of having more thresholds and therefore more borderline. But I wonder also if the complexity of the response, has to also increases the the amount of effort that has to go into the bag of words and creating the number of inputs. So that's why I'd say I wonder if it's just linear in the number of categories, or maybe it's polynomial in the number of categories, and also in terms of time and so on. So I think it's well beyond what you need to do now, but I think looking forward, it would be good to have some sense of how the additional complexity affects the operating characteristics of the system.
Yeah. We might need more training data, but yeah, it's only 3 or 4 categories, so it's not like it's not a very complex problem because it's a few category learning, so it's not like image captioning or labeling or something like that. So it's probably still pretty manageable.
Yeah, I have the same idea. Yeah, for the current study, I used like 8 countries in this research, but in another like exploration, when I included or like more than 50 countries, the scope was increased to all languages, but it just took 1 hour to run the model itself. So the running the model does not like that becomes super complicated if we have like partial credit or if we have like more languages. So I think it's still manageable. Yeah. So,
How do you want to ask your question, maybe?
let me
Yeah,
see.
I put something in the chat, and I think Ella asked me the question before me, so I'll
Oh,
repeat
okay.
the question first, which is, did you systematically evaluate the quality of the machine translations? Seems like it would be difficult to identify misspellings in different languages, like you showed for Korean. And then,
Thank you.
sorry, I added on that saying that you mentioned the correction of misspelling as one of the early pre-processing. So I wonder, is it done on English or on the original language? Because if it's on English, then the responses have already been translated from other languages. So machine learning translation shouldn't contain any misspelling, right? And then if it's done on the original language, then does that mean you did miss the correction for misspelling for every language? And I'm asking also because you previously asked me about some Chinese characters that are easily misspelled and translated into completely different things. So I just wonder how you were able to address this in the end.
Okay, thank you so much for a lot of questions. Okay, I think okay, I think I need to go one by one.
Okay.
So the first question, yeah, from Ella. So about the systematic evaluation of the quality of the machine translations. And actually we did not like go through in-depth evaluation of the machine translation, but in this study we used the languages that we can ask for help for the native speakers in the Teams and Pearl Study Center. So for me, I looked through the overall translations in the Korean responses, and also if there look some weird translations, Matthias reviewed some problematic responses. So we were able to take a brief look at the translation quality, but we did not evaluate systemically about the machine translations. But we were more focused on if there is any misalignment between human and machine scores. We look through those responses to see if it comes from the translation issue or it comes from any other model relevant issue. So we were more focused on the analyzing or reviewing the responses that have misalignment between human and machine scores. Yeah, so that might be the answer for the first question. Matthias, do you want to add anything
Yeah,
to this
yeah,
one?
I will add something almost a little blasphemic. Even if we would mistranslate every word from a language that we don't know, but we would do so consistently, and we would then train a machine to score that based on human scores, we would still be okay. Fortunately, that is not the case. So many of these machine translations are actually quite smart. So they actually are relatively resistant even to misspelling, unless it's a single word. So then you can't do much. If a single word is misspelled, you don't have context, you don't have anything. It gets a little bit better when you have the context of the item even. But you can also evaluate it based on, say, some form of reverse evaluation. Does it produce more or less the same vocabulary or bag of words when you translate all of the responses? Or does it translate into completely different bag of words? Is the agreement high? Is more or less the length okay? Do they translate all the words? So is everything in the end English? So you can have all kinds of indirect measures. But for the first study, as Jenny mentioned, we looked at languages that we actually speak in the center. So we could look at, beyond Korean and German, Chinese, obviously, Turkish, French in theory. I don't know whether we had that and asked.
Turkish, yeah.
Turkish and maybe a few more languages that we could easily grasp in terms of just having somebody in the center who can speak those languages. So there you can have a direct comparison, and then you can do these kinds of indirect checks of quality of translation, whether you get the same set of words, the bag of words, whether you get similar lengths, whether every word is translated, whether you get high agreement at the same level. And people who have high scores on other items should also get high scores on that item if the translation is right. So you can do a lot of checks along those lines.
Yeah, I think also Jenny made a good point that actually if there's high agreement between human and machine score, then we can pretty confidently say that probably the translation is good too, because otherwise you won't achieve such agreement, right? So I think, yeah, that makes sense to me. But Ella further asked if you used the full sample or did you compare the bag of words across countries?
Oh, let me see.
Sorry, I'm speaking for you, Ella, but you can, yeah, feel free if you want to say first of all.
Well, there might be also other questions, but I think, well, Jenny, as far as I remember, you tried out language-dependent models and also across language models. The initial work was really to try out all kinds of variations, to train it by language and train it across languages.
Yeah.
So, as far as I remember, you did a lot of stuff.
Yeah, we did a lot of exploration, and in this research, we applied the same bag of words model across languages to ensure the consistency. So this is how we machine score the student responses in the testing data set based on the same key feature matrix from the training model. So that is the answer for the question. And regarding the,
I would like to know how how you decided on the sample text to translate.
sample text.
You know, the content of text that you are researching to translate. The paragraph or sentence or something that the content of text that you're trying to translate. How did you decide what to translate? Because I see like if you are if there are elementary school level, high school level, college level, and there's like professional writing and stuff. You will have a different depends on the input text. You'll have a different level translation.
So those were all items from International Mathematics and Science Assessment, and the text to be translated are the responses to these items in different languages from a sample of students taking these items in different countries. So we looked through the test more or less and found those items where you needed an open-ended response and where we thought that those are good candidates to try this automated scoring, where the response is relatively constrained. It's a short written response, to be able to then train a machine to provide human scores, to provide computer-based scores that can be compared to human scores.
I see. All right. Thank you.
Yeah, these items are grade 4 items, and the responses are domain specific. So in terms of the word frequency, we can see high regularity, like including the certain keywords. So this response will be a good starting point to try out the Bagel words model, because it can effectively capture the key terms that frequently appear in the responses. So based on this response set as a starting point, we can move to grade 4, or in the future,
All right. Thank you.
thank you for the question. Okay. There's another from Caroline.
I just made a comment about translating, the job of, I'm sort of more about creating these tests. And, a big problem would be the translation of the original items to the many, many languages that you need to do this to. And using this ChatGPT translation seems so good. I really was amazed. I didn't know about this. I had always used Google or something else before, and it just looks so much better that you would want to use it to help you do these translations, at least to kind of do the first draft of them and then have humans. Maybe somebody here is doing that work and has a comment on that process and whether the new AI translations are being used to help that. But maybe that's not the topic here. As far as,
it's we were also surprised.
So
we don't know how well it goes in the other direction too. From other languages to English, it seems to work pretty well. We didn't try the other direction, so we didn't use English responses and translated them to Azerbaijani, for example, or something like that. So
that's right away what I'm thinking. It's like saving money, and then the other one was really, I think Henry or somebody might have also referred to this, and that is using greater response or something, rather than just dichotomous, to take this to the next level, and to use all the information that's in these answers to, and not just to grade the person, let's say, more fairly, but to actually learn about the items and whether the responses are being differential according to these cultures, that you might learn something or be able to learn it more efficiently, using, a finer grade scoring model at some point in the future. Is that part of the future research planned?
Yeah, I think we can definitely consider like more like classification category items, and we can also consider the expand the scope to multiple languages. So I think this is a good starting point, and we can consider more directions how we can expand the scope of automated scoring to more different CR items, more different types of languages. I think there are so many things we still need to explore, and I'm really excited to move forward.
One
Thank
question.
you.
All right, so one question, do you think the model could possibly extend to like variations of language. I'm thinking in the context of, so I'm from Jamaica and we speak the official language of English, but say for instance, the test is conducted in schools and it's a rural area and the student writes, well, our dialect, we have a dialect, but if a student writes, it's like broken English, could the model make sense out of what the student writes?
That's a good one. I would expect it that given how these models are trained, being essentially on that you might. Jenny mentioned this low resource languages, so I don't know whether it's exactly that case, but it might be, say, local dialects or certain group dialects or something like that. That this could be a very good, interesting area of research, how well these kinds of systems are at that. Even, yeah, processing these dialects, being able to maybe translate it into other dialects. So again, this is also true for other languages, not only English, where you have local dialects. So we have, for example, I don't know how many versions of Arabic, even how many language versions of Spanish, Portuguese, even German, French, certainly English. If you look across the globe, there are many different countries where English is used. There are all local variations of those, and it would be a very nice exploration to do a specific study around that, or maybe there's always the next dissertation, right? So that could be interesting. So it's
Yeah,
not
I think
particular.
that is really.
Yeah. Sorry, Jenny. Please go ahead.
No, it's okay. Yeah, I'm really curious how ChatGPT or Google Translate works for the local dialects, because I think that would be the similar case for the low resource languages. But these days, big tech companies invest more and more on the building the corpus for the low resource languages and the dialect. So I'm curious how it works with the machine translation. Yeah.
But that's a very interesting question. Honestly, I think it's a really inspiring one, because again, we are running out of time slowly, but because this is a topic about how do we abstract from, say, local variations in spelling and pronunciation. So this is a really nice topic. We are out of time. If there are questions, please send an email. And thank you everybody for attending.
Thank you so much for listening.
Thanks very much. Excellent.
Thank you.
Excellent.
Thank you.
Thank you.
Thanks.